Atoms are made up of protons, neutrons, and electrons. Protons and neutrons are located at the center of the atom, in the nucleus. Electrons surround the nucleus at varying distances, and they can be divided into core electrons and valence electrons. Core electrons are tightly bound to the nucleus, and valence electrons are the outermost electrons. They're also involved in all chemical reactions. The number of valence electrons varies by element. For the main group elements, the number is equal to the group number that the element belongs to. For example, sodium belongs to group 1A, so it has 1 valence electron. Bromine belongs to group 7A and has 7 valence electrons. We represent valence electrons using a Lewis dot symbol. Each element's symbol is surrounded by dots, which represent its valence electrons. For example, oxygen has 6 valence electrons, and this is its Lewis dot symbol. Each dot represents one of oxygen's 6 valence electrons. Neon has 8 valence electrons, and this is its Lewis dot symbol. Carbon has 4 valence electrons, so its Lewis dot symbol looks like this. Next, we'll explore the octet rule. Noble gas elements in group 8A have either 2 valence electrons, like helium, or 8 valence electrons, like neon, argon, krypton, xenon, and radon. These elements are extremely stable because they have full valence shells. 2 electrons for helium in the first row and 8 electrons in each of the latter rows for the other noble gases. All of these gases represent the octet rule, which states that elements tend to react in a way to attain the same electron configuration as group 8A, the noble gases. Put another way, each atom wants to combine with other atoms until it reaches 8 electrons in its valence shell. Atoms reach 8 electrons by sharing electrons through covalent bonds. Metallic elements at the left side of the periodic table tend to lose 1 or more electrons and form positive ions, such as sodium and magnesium. Each of these has the same electron configuration as the noble gas that precedes it. Nonmetals at the right side of the periodic table tend to either gain electrons to form negative ions, such as fluorine, oxygen, and nitrogen, or to share electrons in covalent bonds. When nonmetallic elements react with each other, they share electrons in order to reach 8 valence electrons. Let's see this in action. One fluorine atom has 7 valence electrons, so it requires 1 more to satisfy the octet rule. Fluorine gas, or F2, shares electrons between 2 fluorine atoms. The left fluorine atom now has a total of 8 electrons around it, as does the right fluorine atom. The shared electrons form a covalent bond. Any unshared electrons are called lone pairs. The 2 electrons that form the covalent bond are often represented by a single line. We can represent the fluorine gas molecule by using a line and dots to show the bonding pair and the 6 lone pairs, respectively. This is called a Lewis dot structure. Some atoms have to share more than 1 electron in order to satisfy the octet rule. Let's look at oxygen. Each oxygen atom has 6 valence electrons, so each one requires 2 more electrons. The left oxygen atom now has a total of 8 electrons around it, as does the right oxygen atom. The 4 shared electrons form a double bond, which is represented by 2 single lines. Remember, each line in the Lewis dot structure represents 2 electrons. Hydrogen is an exception to the octet rule because it only needs 2 electrons to be stable instead of 8. In this example, this hydrogen atom has 1 valence electron, so it requires 1 more. The fluorine atom has 7 valence electrons. It requires 1 more to satisfy the octet rule. The hydrogen atom now has a total of 2 electrons, so it's stable. And the fluorine atom now has a total of 8 electrons around it, so it's also stable. The Lewis dot structure of this hydrofluoric acid molecule shows a line and 6 dots. This represents the bonding pair and the 3 lone pairs of the electrons. Now let's review the rules for writing Lewis dot structures. Rule number 1 is, add the number of valence electrons for each atom in the molecule together. Let's use carbon tetrafluoride as an example. Carbon has 4 valence electrons and fluorine has 7 valence electrons. Therefore, the total number of valence electrons is 4 plus 4 times 7, which equals 32. The second rule is, write out the elements of the molecules so that the least electronegative element is in the center and is surrounded by the other elements. Again, we'll use carbon tetrafluoride as our example. Rule 3. Place a covalent bond between the central atom and the outside atoms. Remember, each covalent bond contains 2 electrons. The 4 covalent bonds use 8 of the 32 valence electrons in carbon tetrafluoride. The fourth rule is, add electrons to the outer atoms as lone pairs to satisfy the octet rule. This uses 24 electrons. There are no electrons left, so this is the Lewis dot structure for carbon tetrafluoride. Next, we'll apply the fifth rule. In this example, we're going to use NH3, commonly known as ammonia. We'll start by going through the first 4 rules. Now we can apply Rule 5, which states, if there are still unused electrons, add the lone pairs to the center atom. So we'll place the remaining 2 valence electrons on the central nitrogen atom. This creates the Lewis dot structure for ammonia. Finally, we'll apply Rule 6, which states, check all atoms in the molecule to make sure each one has 8 electrons, with the exception being hydrogen, which only requires 2. If an atom has fewer than 8 electrons, we'll need to create double or triple bonds. It's also important to point out that double bonds only exist between carbon, nitrogen, oxygen, and sulfur. Now, let's apply Rule 6 to CH4, or methane. Hydrogen has 1 bond, which equals 2 electrons, and carbon has 4 bonds, which equals 8 electrons, so both molecules are stable. Let's see how Rule 6 applies to CF4, or carbon tetrafluoride. Fluorine has 1 bond with 3 lone pairs. This equals 2 plus 3 times 2 electrons for a total of 8 electrons. It's now stable. Carbon has 4 bonds equaling 8 electrons and is also stable. Finally, we'll look at formaldehyde. We'll start, as always, by applying the first 5 rules. Finally, we'll apply Rule 6. Oxygen shares one of its lone pairs with carbon. This creates a double bond between carbon and oxygen, and gives carbon the needed 8 electron total. This is the Lewis dot structure for formaldehyde. The octet rule applies to groups 4A through 7A in the second row of the periodic table, but there are exceptions to the rule. Let's take a look at 2 examples, BF3 or boron trifluoride, and PF5 or phosphorus pentafluoride. We'll start by applying the first 5 rules to boron trifluoride. Next, we'll move on to Rule 6, which is where we find the exception. Check the number of electrons around each atom. Each fluorine atom has 8 electrons, but boron only has 6, which makes it an exception to the octet rule. A boron-fluorine double bond isn't an option because double bonds only exist between carbon, nitrogen, oxygen, and sulfur atoms. The result of this exception is the Lewis dot structure for boron trifluoride. Next, we'll look at phosphorus pentafluoride. Just with boron trifluoride, we'll apply the first 5 rules. Then we come to Rule 6, which is again where we find the exception to the octet rule. Check the number of electrons around each atom. Each fluorine atom has 8 electrons, but the phosphorus atom has 10. This is the Lewis dot structure for PF5. Lewis dot structures show how electrons are distributed in molecules. There are 6 rules.
Lewis dot diagrams for binary ionic compounds. So anion Lewis dot diagrams, remember they're going to gain electrons and they're always going to end up with 8 valence electrons. So if you look at fluorine ion would gain 1 electron to fill that one little spot that it had empty.
Which is represented by the white dot.
Right.
You also have to include the ion charge outside of that bracket. That bracket symbolizes that it's part of an ionic bond.
And that there has been something changed. Cation Lewis dot diagrams, on the other hand, because they're losing all their valence dots, or all their valence electrons, they end up with no dots, have the brackets around it with the positive charge on the outside.
So let's try these. Our first example is sodium chloride. We know that sodium is a positive 1 charge and chlorine is a negative 1 charge. And when you do the crisscross method, you get the formula NaCl. How many sodiums? 1. How many chlorines? 1. Now, how do we represent this? Originally, we start with this. These are the valence Lewis dot diagrams that we originally talked about. Sodium with 1 dot, chlorine with 7. Sodium gets rid of its 1, chlorine gains its 1, and thus we draw the ionic compound as so. Together with the charges on top, they represent how many of each element and their charges and the number of valence electrons.
And now they're electromagnetically pulled together to create that ionic bond.
Which means they're stable. Let's try another one, magnesium chloride. So you're taking magnesium with a +2 charge and you're adding it to chlorine with a -1 charge. Reverse crisscross method tells us that our formula should be MgCl2. 1 magnesium for every 2 chlorines. If you have 1 magnesium for every 2 chlorines, you're starting off with this. 1 magnesium with 2 valence electrons and 2 chlorines with 7 valence electrons each. Together, when they undergo ionic bonding, they give you this. You're noticing your magnesiums have no electrons, no valence dots, but they have a +2 charge. Then we have a big 2 outside of the bracket for your anion, the chloride. That big 2 says that there are 2 of them, which is reflective of what is in the formula.
So aluminum oxide, you're going to do a similar pattern, except again we're going to do the least common multiple in this case. But when you crisscross the aluminum ion and the oxide ion, you get Al2O3, which means we need 2 aluminums and 3 oxygen. So you notice that aluminum has 3 valence electrons. Each oxygen has 6 valence electrons. So when you put these together to create a bond, the electrons from the aluminum atom go towards the oxygen atom and fulfill its octet. You put the big numbers in front of the Lewis dot diagrams of the ions to represent how many of those ions we have in the compound.
But the trend remains the same. You will have no dots next to your metals, 8 dots next to your
Non-metals.
nonmetals, and you have to make sure the charges are written in.